Good day, everyone! Today, we will be discussing an important aspect of aquaculture, the selection of stocks and stocking practices. Choosing the right aquatic species and following proper stocking methods are essential for maintaining healthy populations, ensuring optimal growth, and maximizing production. In this presentation, we'll explore the key factors in selecting quality stocks and the best stocking strategies for sustainable aquaculture. When selecting fish species for aquaculture, several factors must be considered to ensure high survival rates, efficient growth, and market viability. Let's go over some key factors, which are the growth performance, reproductive habits, egg and larvae requirements, nutritional needs and feeding habits, polyculture possibilities, adaptability to crowding, disease resistance, and market demand. By carefully considering these factors, we can select the best species for sustainable and profitable aquaculture. Growth performance is a crucial factor in aquaculture because it directly affects production efficiency and profitability. Let's break down the key aspects. First is high growth rate. Fish species with naturally fast growth rate reach harvest size quicker, reducing production time and cost. Next, grown to marketable size in a short time. The selected species should be able to grow to a desirable size within a short culture period to maximize profits and meet market demand efficiently. Lastly, it should reach marketable size before first maturation. If fish mature before reaching the ideal harvest size, energy is diverted from growth to reproduction, which can slow growth and affect overall yield. By choosing species with excellent growth performance, we can improve productivity and ensure a sustainable aquaculture operation. Reproduction is a key factor in aquaculture because it ensures a continuous supply of fish stock for farming. Let's discuss the important aspects of reproductive habits in aquaculture species. First, the ability to reproduce easily, especially in confinement, is a primary requirement. Species that can reproduce in controlled environments such as hatcheries or ponds are preferred since they provide a reliable stock without relying on wild populations. Next, for a successful culture, a stable supply of seed or young must be available. Consistent availability of high quality juveniles is essential for maintaining a steady production cycle and avoiding gaps in stocking. Next, the reproductive process of the species must be understood, and genetic selection and improvement must be possible. Knowing how the species reproduces allows for better breeding management, selective breeding for desirable traits, and overall genetic improvement for faster growth and disease resistance. Next, reproduction should produce large quantities and occur frequently, or high spawning frequency and fecundity. Species with high reproductive rates ensure a sufficient stock supply, reducing the need for frequent wild seed collection and improving production stability. Lastly, eggs and larvae need to be large, hardy, and easy to culture. Larger and more resilient eggs and larvae have higher survival rates, making the rearing process more efficient and reducing early stage mortality. By considering these reproductive factors, we can ensure a sustainable and efficient aquaculture system. After considering reproductive ability, the next important factor in species selection is understanding the nutritional needs and feeding habits of eggs and larvae. Proper nutrition during early life stages is critical for survival and growth. After reproductive ability, the next factor to consider when selecting an aquatic species to culture is nutritional needs and feeding habits. Eggs and larvae require appropriate nutrition to develop properly. Understanding their feeding needs help ensure high survival rates and strong growth performance. For feeding habits, a species that can be selected low on the food chain or high on the food chain. Some species feed on lower trophic levels, such as algae or plankton, while others are carnivorous and require more expensive feed. Choosing the right species affects overall production cost. An aquaculture species low on the food chain consumes low-cost feed or low-cost vegetable matter or indirectly consumes primary foods within the pond. Species that feed on naturally occurring pond organisms or plant-based diets are more cost-effective to culture, making them ideal for sustainable and economical aquaculture practices. By selecting species with manageable feeding habits and nutritional needs, we can improve efficiency and reduce cost in aquaculture operations. Proper nutrition is essential for the growth, health, and overall success of aquaculture species. Like terrestrial animals, aquatic animals require a balanced diet, but their feeding habits and nutritional sources differ significantly. First, aquatic animals like terrestrial animals require protein, carbohydrates, fats, vitamins, and minerals. These nutrients are essential for energy, growth, and immunity, and overall health just like in land animals. Unlike terrestrial animals, some of the nutritional needs are met directly from the aquatic environment. Many species can obtain natural food sources like plankton, algae, and detritus, reducing the need for supplemental feeding. Next, research on the optimal amounts and forms for each species continues. Scientists are continuously studying species-specific dietary needs to improve feed efficiency, reduce weights, and enhance growth rates. Next, the more completely nutritional needs are understood, the more efficiently other aquatic animals can be produced. Better knowledge of nutrition leads to improved feed formulations, higher survival rates, and more sustainable aquaculture practices. Lastly, ability to accept an artificial diet. Species that readily consume formulated feeds are easier to manage in aquaculture settings, making production more predictable and cost-effective. By understanding and optimizing nutritional needs, we can enhance aquaculture efficiency and sustainability. Polyculture is the practice of raising multiple species in the same production system. This approach can enhance resource efficiency and maximize productivity. However, the choice of species for polyculture depends on the production system being used. Selecting polyculture as a criterion for determining which species to produce depends on the type of production system. Some species are better suited for polyculture than others, depending on whether the system is extensive, semi-intensive, or intensive. For an intensive culture system, such as trout or catfish production, growth rate could be more of a concern than the efficiency in use of water space and nutrients. In high-density, intensive farming systems, maximizing growth rate and feed conversion is prioritized over optimizing space and nutrient cycling. Polyculture increases the total aquatic production in a volume of water by using species that occupy different dimensions of the water and feed on different feedstuffs. By combining species that utilize different water layers and food sources, polyculture reduces competition, improves resource efficiency, and increases overall yield. When planned correctly, polyculture can improve productivity, reduce environmental impact, and create a more sustainable aquaculture system. In aquaculture, space is a valuable resource. To maximize production, species must be able to tolerate high stocking densities without experiencing excessive stress or health issues. Aquaculture requires species that are used to crowding. Species that naturally school or tolerate high densities are preferred, as they can thrive in confined spaces without significant negative effects. Crowding increases the productivity of a space while increasing management for space. Higher stocking densities maximize yield, but they also require careful management of water quality, oxygen levels, and disease control to prevent stress-related issues. Aquatic species selected for culture exhibit adaptability to withstand crowding. Species that can handle crowded conditions without compromised growth or health are ideal for intensive aquaculture system. By selecting species that can adapt to crowding, we can improve efficiency while maintaining a healthy and productive culture environment. Disease resistance is a critical factor in aquaculture as diseases can lead to high mortality rates and significant economic losses. Selecting species with strong natural immunity can improve production success. Species vary widely in their ability to resist disease. Some species are naturally more resilient to pathogens, while others require intensive health management to prevent infections. Aquaculturists select species for disease resistance based on the conditions at their production site. Environmental factors such as water quality, temperature, and stocking density influence disease risks. Farmers choose species that can thrive in their specific conditions with minimal disease outbreaks. By prioritizing disease-resistant species, aquaculture operations can reduce dependency on antibiotics, lower mortality rates, and enhance sustainability. Even if an aquaculture species is easy to produce, its success ultimately depends on market demand. Without a strong market, production efforts can go to waste. Several factors influence whether a species is profitable. First, desire by consumers. The species must have a strong consumer preference, whether for taste, nutrition, or cultural significance. Next, price consumers can afford. The product must be competitively priced to match consumer purchasing power while ensuring profitability for farmers. Next, prepared, easy to use forms of the product. Value added products such as fillets, frozen portions, or ready to cook options increase marketability and convenience for consumers. Next, storage to reach consumers. Efficient supply chains, proper storage, and distribution networks ensure that the product remains fresh and accessible to buyers. Lastly, desired flavor. Species with good taste and texture are more likely to be preferred by consumers, increasing demand and sales potential. Understanding and responding to market demand is crucial for the success of any aquaculture venture. After selecting the right species for aquaculture, proper stocking practices are essential for maintaining a productive and sustainable system. Stocking practices involve determining the right number of fish to introduce into a pond or tank, ensuring they have enough space, food, and a healthy environment for growth. One of the key factors in stocking is the stocking rate, which directly affects growth performance, water quality, and overall farm profitability. Let's explore this in more detail. Stocking rate plays a crucial role in aquaculture management as it directly impacts growth, survival, and water quality. It can be interpreted in two ways. First, stocking rate in terms of number of fish per unit area or volume of water. This method measures the number of fish stocked per square meter or cubic meter, such as 5 fish per square meter or 50,000 fish per hectare, or 23 fish per cubic meter in a cage or 5,000 fish in a 200 cubic meter cage. Next, stocking rate in terms of weight per unit or volume of water. This approach considers the total biomass in relation to available space, such as 0.4 kilogram per square meter, 4,000 kilogram per hectare, or 90 kilogram per cubic meter in a cage, or 420 kilogram in a 6 cubic meter cage. Understanding both interpretations of stocking rate helps aquaculturists manage space efficiently and optimize production outcomes. The appropriate stocking rate depends on several factors that influence fish growth, survival, and overall production efficiency. These include level of production. Higher production goals require precise stocking densities to balance growth, water quality, and resource use. Next, types of food. Availability of natural food sources or formulated feed affects how many fish can be supported within a system. Next, pond unit in the case of pond. The size, depth, and water exchange capacity of the pond determine the ideal stocking rate. Next is the kind of fish. Different species have varying space, oxygen, and feeding requirements that influence stocking density. Lastly is the culture system, like the pond, cage, or pen. Stocking rates differ depending on the type of system, with intensive systems allowing higher densities due to controlled environments. By considering these factors, aquaculturists can determine the best stocking rates for maximizing productivity while maintaining a healthy aquatic environment. Stocking rates in aquaculture vary depending on the species, the production system, and the type of natural food available. This table presents the stocking rates for different monoculture methods in grow-out ponds. First is the extensive culture. Extensive systems have the lowest stocking rates, typically between 2 to 4,000 fish per hectare. These rely mainly on natural food like lablab, lumot, or plankton. For example, bangus with lablab is stocked at 2 to 3,000 per hectare, while sugpo can reach 10 to 20,000 per hectare. Next is the modified extensive culture. In modified extensive systems, stocking rates increase slightly, ranging from 3 to 6,000 per hectare. These systems still rely on natural food but with improved management. For instance, sugpo stocked with lablab can reach up to 25 to 30,000 per hectare. Next is the semi-intensive culture with supplemental feeding. Semi-intensive systems introduce supplemental feeding, allowing for higher stocking rates of 7 to 12,000 per hectare. In these systems, natural food is still used, but artificial feeds help sustain growth. Sugpo, for example, can be stocked at 40 to 50,000 per hectare under this method. Lastly, the intensive culture with complete feeding. Intensive culture systems have the highest stocking densities, often exceeding 50,000 per hectare. These systems rely entirely on formulated feeds to support fish growth. In high production farms, sugpo can be stocked at 60 to 200,000 per hectare, while bangus can reach 15,000 or more per hectare. For key considerations, lablab versus lumot versus plankton. Lablab is a natural food mix preferred for shrimp. Lumot is suited for sigonids, and plankton is used for high-density systems. Next, higher stocking densities require better management of water quality and feeding to maintain fish health and growth. By selecting the appropriate stocking rate and culture method, aquaculturists can maximize production while ensuring a sustainable and efficient farming system. In polyculture, different species are stocked together to optimize space, food resources, and overall production. The stocking rate depends on the level of production, ranging from extensive to semi-intensive systems. First is the extensive polyculture. It relies on natural food and minimal intervention. In extensive systems, stocking densities are lower and the fish rely mostly on natural food sources available in the pond. Here you can see the bangus and mud crab. In this system, 1,000 bangus are stocked along with 500 mud crabs per hectare. Mud crabs help clean the pond bottom and feed on detritus, while bangus consume plankton and algae. For the sugpo and bangus, here 10,000 to 20,000 sugpo or shrimp are stocked with 500 bangus per hectare. The shrimp occupy the pond bottom, while bangus feed in the water column, reducing competition for food. Next is the semi-intensive polyculture. It uses supplemental feeding for increased production. In semi-intensive systems, stocking densities increase and supplemental feeding is provided to ensure optimal growth. The bangus and mud crab. In this setup, 9,000 bangus are stocked with 1,000 mud crabs per hectare. Some natural food is still utilized, but supplemental feeding ensures better growth rates. The sugpo and bangus stocking rates range from 5,000 to 10,000 sugpo along with 4,000 to 6,000 bangus per hectare. The combination works well because shrimp and fish use different parts of the pond ecosystems. Next, we have the grouper, mud crab, and saline tilapia. This system includes 3,000 grouper, 1,000 mud crabs, and 1,000 saline tilapia per hectare. Each species has a different ecological role. Grouper as a predator, mud crabs as scavengers, and saline tilapia feeding on plankton and detritus. Next is the intensive polyculture. It relies on complete feeding and high stocking densities. Intensive polyculture requires strict management of water quality, feeding, and disease control. However, in many cases, farms prefer monoculture at high stocking densities to simplify management, which is why no data is provided for intensive systems in this table. In conclusion, polyculture offers a sustainable way to maximize pond productivity by combining species that use different food sources and occupy different spaces. By carefully selecting species and adjusting stocking densities, aquaculturists can create a balanced system that enhances production while maintaining environmental sustainability. In aquaculture, different pond units serve different purposes throughout the growth stages of fish and shrimp. The stocking density varies depending on the pond type, ensuring proper space, food availability, and survival. This table presents the stocking rate for bangus or milkfish and sugpo or tiger shrimp when lablab is used as the primary food source. The nursery pond has high stocking density for early growth. Nursery ponds are used to rear young fish and shrimp immediately after hatching or when they are transferred from hatcheries. Since they are small and require protection, stocking densities are high to maximize survival. For the bangus, 30 to 50 fish per square meter. For the sugpo, you need 20 to 30 post-larvae per square meter. At this stage, Lablab provides an abundant natural food source that supports rapid growth before transfer to the next phase. Next is the transition pond. It is the intermediate phase before grow out. Once the fish or shrimp outgrow the nursery pond, they are transferred to transition ponds, where the stocking density is reduced to give them more space and allow for better growth. Example for the bangus, you need 10 to 15 fish per square meter. For the sugpo, no data was available in the table for this stage. This stage helps the fish adjust to a less crowded environment before moving to the rearing pond. Next is the rearing pond. It is the final grow-out phase for market-size production. In the rearing pond, the goal is to grow fish and shrimp to their marketable size. Since they are larger, they require more space, leading to significantly lower stocking densities. For the bangus, 0.15 to 0.3 fish per square meter. For the sugpo, you'd have 1 to 2 shrimp per square meter. At this stage, Lablab alone may not be sufficient and additional feeding may be introduced to support optimal growth. For the key takeaways, stocking density decreases as fish and shrimp grow, allowing them more space and access to food. Next, Lablab serves as a natural food source, but as the fish mature, supplemental feeding may be required. Lastly, each pond unit plays a specific role. The nursery pond supports early growth, the transition pond helps in adaptation, and the rearing pond is where fish are raised until harvest. By following the appropriate stocking rates in each pond type, aquaculturists can maximize growth, ensure sufficient resource use, and maintain a sustainable production system. Now let's talk about stocking rates based on different aquaculture systems. The density at which we stock fish depends on the culture method used. This table outlines the stocking rates for some common species in 3 systems: fish cages, fish pens, and fish ponds. First is the fish cage culture. It is the floating controlled enclosure. These are net enclosures suspended in open water, allowing continuous water exchange. Since cages limit the space for movement, stocking densities tend to be high but must be carefully managed to maintain water quality. For the bangus or milkfish, they are stocked at 25 to 40 fish per cubic meter for juveniles. For the siganid or rabbit fish, they are stocked at 100 to 200 fish per cubic meter for juveniles. As for the grouper, they are stocked at 30 to 50 fish per cubic meter for juveniles. It is important to note that sugpo or tiger shrimp is not typically raised in cages, which is why it is not included in this category. Next is fish pen culture. They are semi-enclosed structures in natural waters, which are larger than cages and allow fish to move freely in a semi-controlled environment. These enclosures are built in natural water bodies with a minimum depth of 3 meters to ensure good water circulation and prevent overcrowding. For the bangus, they are stocked at 5 to 8 fish per cubic meter at 20 to 25 fish per square meter. For the siganid, they are stocked at 40 to 50 fish per cubic meter at 120 to 150 fish per square meter. As for the grouper, they are stocked at 8 to 10 fish per cubic meter. Because fish pens provide more space and rely on natural water exchange, stocking densities are lower compared to fish cages. This helps minimize stress and improves growth rates. Lastly, we have fish ponds. These are land-based, man-made enclosures where water conditions and feeding are carefully managed. Since ponds allow for different culture intensities, the stocking rates depend on the production method used, whether it's extensive, semi-intensive, or intensive farming. In this table, the stocking rates for fish ponds are not specified, but are instead referenced under another classification that considers food availability and culture intensity. For the key takeaways, we can learn that fish cages allow for higher stocking densities, but water quality must be managed to avoid overcrowding. Fish pens provide more space and rely on natural conditions, so the stocking rates are lower than in cages. Next, fish ponds require active management, and stocking densities vary depending on the culture method. Lastly, each species has unique space requirements, so selecting the right stocking rate is essential for optimal growth and survival. By carefully choosing the appropriate stocking rate and culture systems, we can maximize fish production while ensuring sustainable and efficient aquaculture practices. Now that we've covered stocking rates and different culture systems, let's move on to the computations involved in fish stocking. Proper calculation of stocking density is crucial in aquaculture to ensure optimal growth, minimize competition for resources, and maximize production efficiency. In this section, we'll go through the formulas and methods used to determine the appropriate number of fish to stock based on factors such as pond size, water volume, and production goals. Understanding these calculations help aquaculturists make informed decisions for sustainable fish farming. Let's begin. Now let's discuss how to compute the total number of stocks needed for a pond. Proper stocking density is essential to ensure optimal growth, minimize competition for resources, and maximize production efficiency. To determine the total number of fish to stock, we use this formula. Number of stocks equals to area times stocking rate per unit area. Let's take an example. Suppose the standard stocking rate is 20,000 fish per hectare and we have a pond measuring 50 meters by 80 meters. We will go through three different ways to compute the total number of fish needed. Option 1. Direct calculation using hectare conversion. First, determine the area of the pond. So 50 times 80 is equals to 4,000 square meters. Next, apply the formula. Number of stocks is equals to 4,000 square meters times 20,000 fish times 1 over 10,000 square meters is equals to 8,000 fish. So, based on the first method, we need to stock 8,000 fish in this pond. For the second option, convert stocking rate to per square meter first. Determine the area again. 50 times 80 is equals to 4,000 square meters. Convert the stocking rate per hectare into stocking rate per square meter. So, stocking rate per square meter is equals to 20,000 fish over 10,000 square meters is equals to 2 fish per square meter. So, calculate the total fish stock required. 4,000 square meters times 2 fish per square meter is equals to 8,000 fish. Again, we arrive at 8,000 fish using this method. The third option is to use ratio and proportion. First, set up the proportion equation. So, 10,000 square meters over 20,000 fish is equals to 4,000 square meters over x. Now, let's solve for x. X is equals to 4,000 square meters times 20,000 fish over 10,000 square meters. So, x is equals to 8,000 fish. Once again, using ratio and proportion, we confirm that the pond should be stocked with 8,000 fish. For the key takeaways, no matter which method we use, we arrive at the same answer. 8,000 fish should be stocked in a 4,000 square meters pond at a standard rate of 20,000 fish per hectare. These computations are essential to maintaining a balanced and productive aquaculture system. Stocking too many fish can lead to overcrowding, poor water quality, and slow growth, while understocking may result in inefficient use of resources. In the next section, we'll explore other key stocking calculations to further refine our stocking strategies. Now, let's move on to another important aspect of fish stocking, the determining the principal or total number of stocks needed, as well as calculating the percentage survival, motility, and survival rate of stocks. These computations help us plan for losses and ensure we have enough fish to sustain production. First, we have the finding the principal or total number of stocks. In aquaculture, not all fish are stocked will survive until harvest. Some will be lost due to various factors such as handling stress, predation, or environmental conditions. To account for this, we must determine the total number of fish to purchase, including all allowance for mortality. An example scenario, a 4-hectare grow-out pond requires 128,000 bangus fingerlings for the whole year, with 4 production cycles. If this number represents only 70% of the total fish purchased, since 30% mortality occurs before reaching the grow-out pond, how many bangus fry should be purchased initially? For the formula, we will be using principal or total number of stocks is equals to number of stock survival over survival rate of stocks times 100. So for the substitution, 128,000 fingerlings over 0.70. So 182,857 bangus fry. So to ensure that 128,000 bangus fingerlings make it to grow out ponds, we need to start with 182,857 fry, factoring in the 30% expected mortality during early stages. Now let's determine the percentage survival of stocks. This tells us what portion of the total purchased fry successfully reached the grow out stage. An example question: if 70% of the 182,857 bangus fry survived after rearing, how many fingerlings successfully made it? For the formula, we will use percentage survival of stocks equals to principal or total number of stocks times survival rate of stocks divided by 100. So for the substitution, we have 182,857 times 0.7 is equals to 128,000 bangus fingerlings. This confirms that 128,000 fingerlings survived from the initial 182,857 fry purchased. Next, let's calculate the survival rate of stocks. This tells us what percentage of the original number of fry survived after being raised in nursery and transition ponds. For the example question, if only 128,000 bangus fingerlings survive out of the 182,857 fry purchased, what is the survival rate? For the formula, we will be using survival rate of stocks is equals to percentage survival of stocks times 100 over the principal or total number of stocks. For the substitution, we have 128,000 times 100 over 182,857. This equals to 70%. So the survival rate of our stocked fish is 70%, meaning we accounted for a 30% mortality rate in the nursery and transition ponds before the fingerlings reached grow-out ponds. For the key takeaways, first, stocking calculations must factor in expected mortality to ensure the required number of fish reaches the grow-out stage. Next, survival percentage and mortality rates help in adjusting stocking plans for future cycles. Lastly, accurate stocking computations ensures efficient use of resources and better production outcomes. Understanding these calculations allow aquaculturists to optimize their stocking strategies, minimize losses, and maximize productivity. Now that we've covered the computations involved in fish stocking, let's move on to the next important aspect: stocking techniques. Proper stocking methods ensure that fish adapt well to their new environment, reducing stress and mortality while promoting healthy growth. In this section, we will discuss different stocking techniques, including best practices for handling, acclimatization, and distribution. These techniques play a crucial role in maximizing survival rates and improving overall production efficiency. Let's dive into the details. First, prepare the pond. Before introducing fish, it's essential to refresh the pond with tidal water at least a day in advance. This process improves water quality by replenishing oxygen levels and removing waste buildup. Second, stock at the right time. To minimize stress caused by heat, fish should be stocked early in the morning or during the evening when temperatures are lower. Cooler conditions help reduce metabolic stress and improve survival rates. Third, acclimatization process. This step ensures that the fish gradually adjust to their new environment. Fry are first transferred to a white plastic or porcelain basin for observation. Unwanted species that may have been mixed in during transport are removed. Salinity and temperature levels of the transport and pond water are measured and compared. If salinity difference exists, adjustments should be made slowly, not exceeding 5 parts per million per hour to prevent shock. Providing aeration in the basin ensures the fry receive enough oxygen. Fry are counted to monitor stocking accuracy. Lastly, direct stocking method. If fry are stocked directly from transport bags, the bags should be floated in the pond for about 10 minutes to equalize temperature. Small amounts of pond water should be added gradually into the bags to allow salinity adjustment. Finally, the fry should be evenly distributed across different areas of the pond to prevent overcrowding and competition. By following these stocking techniques, fish experience lower stress levels, leading to higher survival rates and more efficient production in aquaculture. As we conclude this presentation, we have explored the essential factors in choosing fish for aquaculture: stocking practices, and proper techniques to ensure high survival rates and sustainable production. From understanding growth performance and market demand to mastering stocking computations and acclimatization, these principles are key to a successful aquaculture operation. By applying these practices, we can enhance fish growth, minimize losses, and optimize productivity, ultimately contributing to a more efficient and profitable aquaculture industry. Thank you for your time and attention. May this knowledge guide you in making informed decisions and achieving success in your aquaculture endeavors.